Hello, everyone. I'm Zhen from Cornell University. Today, I'm going to present our paper, TELEPATH, a Minecraft-based covert communication system. This is a joint work with Vitaly Shmatikov from Cornell Tech. State-level censorship prevents free use of the internet in many countries. Common censor techniques include IP and DNS blacklisting, deep packet inspection, protocol whitelisting, and traffic fingerprinting. Therefore, circumvention systems have been developed to provide covert channels that allow the users to access blocked content through the channel. In order to evade the censorship, traffic generated by the channel should look like a permitted, whitelisted application. One approach is to imitate the communication channel of an existing application, for example, Skype. The user sends covert data using a mimicked Skype protocol. However, high-fidelity imitation of a complex application requires mimicking its correct behavior in any situation, including dynamic responses to network conditions, as well as bugs in implementation. Therefore, it is hard to imitate correctly. Since standalone channels are detectable, the only way to look like an application is to use the application and tunnel the data through the application. At protocol level, the circumvention traffic is indistinguishable from the cover application traffic. However, packet sizes and timing could still leak information. Here's the threat model. The sensor is able to identify network protocols and applications. It can collect both circumvention traces and non-circumvention traces to train classifiers. And it can use the trained classifiers to identify an unknown channel. Therefore, the goal of a tunneling system is to generate circumvention traces that are indistinguishable from normal application traces. A common design of tunneling system is traffic substitution. The cover application encodes raw data, such as videos in a streaming app, into encoded messages, such as compressed video frames. The traffic substitution channel replaces the encoded message with covert data. Since the channel is encrypted, the sensor cannot tell if the message is replaced or not. Common applications include video streaming and audio streaming. We observe that online games can be good cover applications. First of all, there are many different games which can provide diverse network traffic patterns. Second, games have large network traffic share, which means that blocking games would incur heavy collateral damage. Also, current game traffic is usually encrypted by default. Among popular games, we find that Minecraft is an interesting platform for covert communication. Minecraft is widely available and very popular in censored regions. It is common for game users to run their own game servers, so servers are globally distributed. Also, Minecraft provides enough channel capacity for common web application. More importantly, Minecraft is modifiable and has large mod communities. The code is well understood and well documented. Here's an overview. A user in the censored region accesses blocked content by tunneling data through a covert channel provided by modded Minecraft. Let's consider a strawman design that follows existing approaches which use deterministic models to shape network traffic to look like unmodified application traffic. First, it runs an unmodified shadow game in advance to record every function call to the game's network manager and stores the timestamp and sizes of the arguments, which forms the deterministic model we call template. Then the template is sent to both the circumvention server and client. To send covert data, both the client and server follow the template but replace the message content with covert data. We implemented the strawman design, and it generates traffic statistically indistinguishable from real game traffic. Existing classifier based on packet size and packet timing distribution cannot distinguish our Strawman design from real game. However, it is still easily detectable. Why? First, we observe that even if the Minecraft traffic is encrypted, packet sizes reveal partial game state. Many game events generate network packets with unique packet sizes. For example, when the player is alive, the game client periodically sends packet 27 bytes long. Other events that can be inferred include if the player is dead and when the player responds. These game events correspond to a simple invariant in Minecraft that once the player is dead, it stays dead until it responds. We can easily check if an encrypted Minecraft trace violates this invariant. Another game event can be inferred is map update. And it also corresponds to an invariant that a dead player does not receive map updates. However, traditional traffic substitution is not aware of this invariant. As a result, the Strawman design may violate these two invariants. Here is a trace generated by the Strawman design that is impossible in a real game. We can see that at the beginning of the trace, the player is dead, and near the end of the trace, we can see a map update before a respawn event, which indicates the player received the map update before it got respawned. So a dead player received a map update, which is impossible. This is caused by some minor reordering due to the network condition when following the template. So we can conclude why the Strawman design doesn't work. The game server and client are stateful and non-deterministic. Previous deterministic traffic substitution approaches do not respect causal relationship between messages. To solve this problem, we propose TELEPATH, a Minecraft-based traffic substitution channel without causality violation. In other words, the substitution does not introduce state discrepancies between server state and client state. The key idea is to separate the encoded messages into state-dependent messages and state-independent messages. We only replace the state-independent messages. And we call this method non-disruptive content substitution. Here is an overview of our TELEPATH implementation. Red boxes indicate components of TELEPATH we introduced as Minecraft modifications. The encoder, which sends Covert data, has an interceptor that can filter outgoing messages and rewrite non-disruptive messages with Covert data. And the decoder can identify incoming messages that contain Covert data, extract the data, and call a dummy message generator to generate suitable dummy message whose content was replaced. Next, I will discuss how to identify non-disruptive content. It usually requires game-specific analysis. We generalize two categories of non-disruptive content that can be found in many games. The first category is visual effects, which are the game elements that the player can see but cannot interact with, usually for better player experience. This information is game state independent, so it can be safely substituted. The second category is synchronization message, which is the message corresponding to a periodic action. The synchronization message can be partially substituted by reducing the effective update frequency. Here are some examples we identified in Minecraft. Map update consists of 55% of client-bound bandwidth. The server uses this type of message to send all map areas within the player's view distance to the client. But the player can only interact with areas within a certain range which is smaller than its view distance. Therefore, the non-interactive map areas are visual effects. Notice that when a player moves, non-interactive areas may become interactive. We solve this issue by sending the changes as Covert data. An example of synchronization message is player position update, which consists of 80% of server-bound bandwidth. The game client periodically sends the player's newest position to the game server. Notice that player movement is continuous. So the player position can be estimated based on its recent positions. So we can interleave update messages and covert messages and use interpolation to make up the information lost to substitutions. More non-disruptive content include light update, entity head look, and hand animation. Next, let's look at performance. The throughput is about 1,300 kilobits per second, and 1 to 2 client bound and 1 to 2 kilobits per second server bound. We use TELEPATH to browse 9 popular websites that are blocked by censor in many countries. 8 out of 9 pages loaded successfully, and 6 in under 1 minute. 1 page timed out due to large amount of requests made. TELEPATH can also support audio streaming up to 256 kilobits per second. Please see our paper for traffic analysis indistinguishability. In conclusion, we identify a key challenge in censorship circumvention, that traditional traffic substitution does not work for stateful cover applications. The statistical traffic analysis indistinguishability is not enough for tunneling through stateful applications. To solve the problem, we proposed non-disruptive content substitution and built TELEPATH, the first system that implements a covert communication channel using a complex popular game, Minecraft, and produces traffic that does not violate application-specific invariants. Thank you.
Questions?
Thanks for your talk. It was very, very cool. I was wondering, so you need to run the game to be able to use Telepath, right?
Yes.
Are there any side effects in the game from this? Can you see like some, for instance, different effects in the game because this is happening?
No. So in our evaluation, we used a Minecraft bot, an automated gameplay, which is very common in Minecraft gameplay. So, we show that in the paper, it is indistinguishable from a real game traffic. So I think that is that's a stricter goal for the cover channel, because usually Minecraft gameplay is more diverse.
Okay, but I was wondering, like, if, for instance, other people are playing on the same server, including people that want to make sure you're not using Minecraft to communicate stuff.
Oh, yeah. So, in our design, we have in the server, we have a list of the user that uses the cover channel. If some player is not in that list, the server will not send any cover data. So it will run exactly the same as a normal game server.
Okay, thanks.
Thank you for this very interesting talk. So I have 2 basic questions. Yeah. So the first one is that in your second slide, you mentioned like there is some IP blacklisting.
Yes.
So I just wonder, like, because you need to communicating between the client and the server, usually which is also using the IP, which is also based on IP. So can your technique solve this IP blacklisting?
So if we assume that game servers are usually not be blacklisted. So because it's games are not sensitive application in many ways. I mean, so yeah. And bootstrapping is also another interesting problem, but usually it's out of scope of this kind of circumvention problem.
Thank you. So my second question is, since we know that the Minecraft, the game provides like the chatting, so the users can chat in the Minecraft. So can we just directly use the chat to send the encrypt or compressed message and decode it on the other client side?
Good question. Yes, definitely you can. But text message channel is usually a limited bandwidth. So if you use the text message channel to do circumvention, either it is very like the bandwidth is very limited, or it can be distinguished through this kind of classification because if you send because if you look at the packet size, there may be some distinguishable characteristics.
Yeah, thank you. Yeah, I'm thinking about this because if we can directly use that functionality, we don't need to mimic the benign server or client.
Yes, but that's not, I mean, if you send a large amount of data through the text channel, it's not a normal game behavior. So because like in our paper, we identified that we can infer game state through encrypted game traffic. So it may be also possible to identify that someone is sending a lot of data through the text channel, which is not normal in real game play.
I see. Thank you.
Okay, one more quick question.
A very cool talk. Quick question.
Yeah.
I was wondering if you did any analysis to see how important it is for you to abide by the game logic. So I see that you try to make sure that there's like no rendering after the player dies and stuff that doesn't break any type of causality. It seems like a lot of effort. I was wondering if you didn't do that, does your traffic now become distinguishable?
Actually, I didn't quite get the question.
Why did you put so much effort trying to make sure it looked like a real game? If you didn't, was it the traffic all of a sudden?
Oh, I see. So basically, if you replace all the traffic of the game, like we showed in the presentation, the trace is detectable. So you don't even need a classifier to do this. It's a one-shot attack. So basically, if you see some event like this, you know this is not a real Minecraft game. So it can be easier detectable than like traditional traffic substitution. Yeah.
Got it. And you can detect that even with it being encrypted?
Yes, Minecraft game state can be inferred even if the game traffic is encrypted.
Thank you.
All right, let's thank the speaker again.